In this video, we will use ProMOL and PyMOL to complete an alignment query using a protein of known function. To begin, I'm going to launch PyMOL. Once again, we see the molecular visualization window, the internal graphical user interface, and the external graphical user interface, running with Xquartz, which enables us to see the plugins on the Mac. Now I'm going to go to the plugin menu and launch ProMOL and bring that window up over here. And we're going to go to the motif finder. So we're going to do a query here. To execute this query, I'm going to enter the PDB ID of a structure. Now I know what this structure is already. So I hit the start button and it comes up and asks me, well, which motifs do you want to run? Well, I don't want to run all motifs. I'll run the P set. Those are the ones that have been designed by my students and myself, and the A set, and these are ones that have been automatically generated using an algorithm one of our students developed. And we're going to take a look at this. I could limit this just to EC class 3, which would speed it up, but I'd rather not do that. So I'm going to select that, and you can see that it's starting the search process. Now this search process is going to take a few minutes. While it's running, I want to introduce some resources to you. So we're going to bring a web browser on the screen, and I'm using Safari because that actually still supports Java, and that'll be important in a moment. Here we are at the Protein Databank webpage, and this is where all the structures that have been released to the public are available, all the protein structures. Now I know the structure that I'm looking at because I started with this, 1AN1. I actually did a search earlier today. What I wanted to find was trypsin, but not one of the trypsins that we have in our library. And so I looked for homologs of one of the trypsins in our library, and I found this one, 1AN1. And if we look at this, we can see on the PDB webpage the identity of the structure. If we scroll down the page, we get some additional information. One piece of information we get here is what's called the EC number. EC stands for enzyme commission, and the enzyme commission number here is 3.4.21.4. Now let's take a look at that site. This is the enzyme commission site, sponsored by the International Union of Biochemistry and Molecular Biology. And EC3, that's a classification of enzymes that are hydrolases. The enzyme commission has 6 classes of enzymes. Hydrolases are enzymes that break bonds using water. Among the EC3 class, we have a lot of different hydrolases, and some act on different bonds. So for example, EC 3.1.2 are thioester hydrolases. Now I know that we're looking at a serine hydrolase that's actually an endopeptidase. That means it cuts bonds with inside the protein, not on the ends of the chains, 3.4.21. And if I separate that out, then I get a list of a lot of different hydrolases. Now if we look at the list, we can see 3.4.21.4 is trypsin. And so I can click on that and it gives a more detailed description. So this is the enzyme commission site that talks about the different EC numbers for proteins. And you may want to use that in the future if you're looking at homologs. This is one way to define homologs, is members of the same EC class. Keep in mind that they're defining homologs here in the EC class based only on the reaction catalyzed, not on the structure of the protein. So that's one resource, the enzyme commission browser. Another resource that I use frequently is called the catalytic site atlas. And on the catalytic site atlas, I actually went here earlier and searched for 1AN1, and it brought this structure up, and it shows, in fact, this is a Java page, and here are the 3 catalytic site residues in 1AN1. We have an aspartate, a histidine, and a serine. And it's possible actually on this page to look things up not only by PDB ID, but if I wanted to find all the proteins that were 3.4.21.4, I can enter that here and search, and it lists a large number. I can't see the number on the page, but I believe there's well over 200 here. So these are some of the things you can do with the Catalytic Site Atlas page. There are links out to other resources as well. And the resources, the PDBE, that's the European version of the Protein Databank, and they have their own features that they emphasize. Also, the PDB Sum is a nice summary page that contains a lot of useful information. So here's the PDBE page for 1AN1, and it describes the structure. We talk about biochemical function here. Focus here on some of the ligands. Ligands are a very important part of the structure. Also modified residues. So this particular structure actually has a D-aspartic acid in it instead of L-aspartic acid. And there are links out here to a lot of other resources that you can use to explore the structure. And this is a resource that I would recommend you use once you take your structure of unknown function and identify some homologs of it. Come look for those homologs in the Catalytic Site Atlas or in the European Protein Databank or in the Protein Databank on the US side. Likewise, you can use the PDB Sum entry to go in and look at things. There's some very nice features here on the PDB Sum page. They have, for example, if you're interested in metals, okay, this protein does have a calcium in it, and it shows the calcium binding site and the amino acids that are bound to that calcium. There's a valine here, asparagine, glutamate, glutamate. So these are different residues that are bound to that calcium item. So there's a lot of useful information on the PDB Sum page. Well, at this point, I'm going to go back and check and see if the query is done in ProMOL. And it is. Well, let's take a look at the results here. I'm going to start with the tree over here. So we have a results tree, and in fact, it's possible to query more than one structure at a time. I just entered one structure in the query box, 1AN1, but you can enter up to, I'm not even sure how many. Typically, students in my research group will typically do somewhere between 25 and 100. If a PDB file has some unusual information or non-standard layout, then it could cause the program to hang. And so we typically don't do more than 100 at a time. But so we have the results for AN1, and it divides the results up by EC class. So the EC class 1, so these are templates in our library that it's comparing 1AN1, and it found that it had some kind of a match. We'll take a look at some of these in a moment. EC2, EC3, and so on. If we look at the numbers here, a 0, that's the Levenshtein score, or the Levenshtein distance between the query structure and the template from the library. In this case, the query value of 0 means that it has all of the residues that are present in the template are found in the query. If we look at a case here where we have a 1, this means that one of the residues in the template is not found in the query. If we have a value of 0 to 4, that means that it depends on how you count. It could involve multiple subunits. It could involve some other measure to say what the Levenshtein distance is. And we'll be actually looking in more depth at these ones in EC class 3 that have zeros. A couple more things I want to emphasize here are a couple of buttons you can use as tools for the alignments you're looking at. I like the Show Alignment tool because this will actually show the alignment between the query and the template structure. We also have a Calculate RMSD tool, and that shows the distance between the different amino acids that make up the active site in the query and the template. So if we start out looking at, let's take a look at one of these ones in EC class 1. Okay, a couple things to notice. First of all, there's a 0 Levenshtein distance, which means that all three of the residues that are found in the template are also found in the query structure. So if we look at the template is in white and the query is in red. So if I click on this tyrosine residue, if I look up now into the external graphical user interface pane, I can see it says you clicked on 1FOH, which is the PDB ID A, that's the chain, tyrosine 289, and I actually clicked on carbon delta 1. And I can do that for all of the template residues. And we see that this template has an arginine and also an aspartate. Now when I look at the query structure, I also get a tyrosine, an arginine, and an aspartate. And so you can see exactly what you're looking at when you click on it. It shows up in the external GUI. So that's one measure of quality, is the number of residues that are there. Now, looking at this, we can clearly see that the alignment isn't very good. The query residues are not very close to the template residues. And in fact, if we look here, when I asked it to do the alignment between one FOH and one AN1 on the screen here by double-clicking on the listing over here in the tree, then it gives the RMSD measurements. That's the root mean squared difference between the structure for all atoms, which is 1.95. Or looking only at the alpha carbons, the value is 2.98 angstroms. And looking at the carbon alpha and carbon beta atoms, it's 2.77. So that's a measure of the distance. We typically consider a good alignment to be something with a value under 1 for the RMSD for all atoms. So that's the alignment between one FOH, which is an EC1 structure. EC1 structures are redox enzymes. Now let's go down here and take a look at a structure that actually belongs to the same EC class as 1A and 1. So when I double click on the template, it's listed here as 1AUJ. We notice that there's a Levenshtein distance of 0, which means that all of the residues that are found in the template are found in the query. If we look up here at the RMSD values, we see the RMSD value for all atoms, which is comparing all atoms in the query to all atoms in the template for the 4 side chains that are shown here. And we can see the value is 0.214 angstroms. And so this is a very nice close alignment. You can also look at it and see that we have a very close alignment. In fact, in some cases, you can't separate the template from the query. The template, once again, is in white. The query is in red. So if we click, for example, here on the histidine in the template, and we click on the histidine in the query, you can see them listed there. They're both histidine 57. One is on 1AUJ. That's the template structure. And then 1AN1 is our query structure. And we can go around and do this for the 4 different amino acids that are found in the active sites. I'm not sure how well you're able to see this on the video, but when you run this on your computer, the lettering here is around an 8-point font, maybe a 6-point font. So it's small, but it's readable. And so this tells us that we do have a very nice alignment between these 2 structures. Now this is 3.4.21.4. That's EC class for 1AUJ. That's also a trypsin. Let's try the alignment for another serine protease, but it's 3.4.21.68. When we compare 1AN1, our query, with 1RTF, the motif in this case, or the template in this case, we see once again we have a Levenshtein distance of 0, which means that all the residues in the query are the same as the residues in the template. We go over here and look at the RMSD values. We can see that the RMSD values are slightly higher, 0.365 for all atoms, compared to a value of around 0.2 when we looked at comparing 1AN1, which is a trypsin, with another trypsin molecule, 1AUJ. But we can see once again that all 4 residues here actually align very nicely. They're not quite as close as they were in the previous case, but it's still a very nice alignment. Now, as you're preparing a report, you probably will want to go in and capture a picture of this. So you can just save image as, we'll save a PNG file, and once again I'm going to do this to my desktop, and I'll say query of 1AN1 against 1RTF, and save that to my desktop. And it comes up in preview on the Mac. And so there's a picture and image that you might want to save for a report you generate. Now we've already looked at some additional resources. I did want to point out one more. So we're going to go back to the Protein Databank website. So this is 1AN1. And one of the things that is very commonly used is a FastA sequence. You'll be using this when you do blast searches with a structure. And if you click on this, you see the FastA sequence for the structure. And in this particular case, we have 1AN1. This is the trypsin molecule. And the second chain here is actually an inhibitor. When I say a FastA sequence, FastA format is pretty simple. The first line starts with a greater than sign, and then it contains information about the structure. And any program that uses FastA files ignores this first line, maybe uses it for information, but doesn't use it for sequence comparison. And then the remainder of the FastA file is simply the sequence of the protein in one-letter characters. So I is isoleucine, V is valine, G is glycine, and so on and so forth. So that's a file that you will need to use when you go to do blast searching. And in our project, we're working with structures of unknown function, but the structures are known and the sequences are known. So you can get a sequence for a structure of unknown function from the PDB website. And that marks the end of this video.